Hi and welcome to Brokabiantrix. So again today in today's video we are going to talk about principle of superpositions. We are going to talk about composite bars, and we are also going to solve problems on deflections. Right. So without any further ado, we'll start with the first problem. A steel bar of cross section. So they have given the cross section as 500 mm square. Is acted upon by the forces shown in figure. Alright, so okay, determine the total elongation of the bar. They've also given the E as 2 into 10 to the power of 5 Newton per mm square. Right, so with this prior knowledge, we'll start with the problem. So here we have a bar. In this, we can divide this particular bar in multiple sections, right? So let us only consider the portion AB. So in the portion AB, let me draw the free body diagram of AB first. Right, so if I draw that, so this is how it's going to look like, right? So in the left hand side I have 50 kilonewton force tensile, and in the right side I should have 50 kilonewton, right? The principle of superposition in equilibrium, assuming this particular body is in equilibrium, the forces acting towards LHS will be equal to the forces acting towards RHS, right? So just for confirmation, 50 plus 10, we have 60 at LHS towards left direction, and towards right directions we have 45 plus 15, again we have 60, right? So in the right directions again we can make use of 50 kilonewton, and that's not going to be a problem. And next, the length of AB portion is 0.6 meter, right? And the area is constant throughout, that is 500 mm square. Now with this particular information we can solve the deflection of particular body AB, that is delta AB. So in delta AB, that is nothing but delta is given by PL divided by AE. So here L is the length of AB, right? So let me just substitute all the power values here. P is nothing but 50 into 10 to the power of 3 into L is 0.6 into 10 to the power of 3. I'll be keeping all of the units in mm. Divided by A is 500 mm square into E is 2 into 10 to the power of 5. Now upon simplifications, let me just cancel out these things. 10 to the power of 3, 10 to the power of 3, 10 to the power of 5, and 1 0 gone, and 2 1 times is 25, and I'll have 25 into 0.6 divided by 50. Now with these things I can write it as, and again 25 and 50 will be cancelled out, and 2, and the final remaining is 0.3 mm. Note that is positive, meaning that it is elongation. Right, so again similarly for, I'll write the free body diagram for BC now. Now in the BC, the length of BC is 1 meter. Okay, so this is going to be 1000 mm, and the forces, right? So here there is a compressive force at B, that is 15 kilonewton, and towards C it is again 10. Let me just go from the left hand side. Here 50 minus 15, right? So again I'll be having a tensile force here, so that is nothing but 50 minus 15 is nothing but 35. So I'll have 35 in the LHS, and in the RHS I'll have the same 35 again, right? So again if I go with the RHS from the right hand side, again I'll have 45 will be the tensile force, minus 10 I'll be getting 35 here. The same thing, the left hand side and the RHS will be equal if the body is in equilibrium, right? With this, again this is kilonewton, this is also kilonewton. Let me just calculate delta BC here. So that is nothing but P into L BC divided by AE. Now if I just directly substitute, I'll have 35 into 10 to the power of 3 into 1000, that is 10 to the power of 3, divided by 500 into 2 into 10 to the power of 5. And if I simplify this, I'll be getting 0.35 mm as the answer. Again, this is also elongation. Right, so finally the last body we have CD. Now if I write the free body diagram of CD, I'll be having the total length is 1.25 mm, that is nothing but 1.25 into 10 to the power of 3, that is 1 2 mm. Okay, and the force here we have 45 kilonewton. This is where also we'll have 45 kilonewton. Right then, so delta CD will be equal to P into L CD divided by A into E. Now P is nothing but 45 into 10 to the power of 3 into L is 1250 divided by 500 into 2 into 10 to the power of 5. So now if I simplify this, I'll be getting 0.56 mm. Now according to principle of superposition, what does that say? It says that the total elongation of the body will be equal to the individual elongations of each portions. So that is nothing but delta of the total body will be equal to delta AB plus delta BC plus delta CD. So which is nothing but 0.3 plus 0.35 plus 0.56. Note that all of these bodies are in tension, so that all of these three portions are elongated. So if I just add all of these up, I'll be getting as 1.21 mm as the total elongation of the body. Right. So let me move on to the next question. So here again, this is also a similar problem, but here we have a body with different cross-sectional area. Right, so again, a member ABCD is subjected to point loads as shown below. Calculate the force P necessary for equilibrium. Calculate the modulus of elasticity, the taking modulus of elasticity as 2.05 into 10 to the power 5 Newton per mm square. Determine the total elongation of the member. Okay, so again, we'll have to calculate the delta. They have given us E, that is 2.05 into 10 to the power of 5 Newton per mm square. Right, anyway, again we'll go with a similar strategy of writing the free body diagram of individual bodies. Before that, let me just calculate P quickly. So the left hand side, forces towards left, that is 10 plus 40 will be equal to the forces acting towards right. So that is P plus 16. Right, so here 50 minus 16 is nothing but P will be equal to 34 kilonewton. Right, so the direction is towards right. Okay, so now let me just give all the names here: A, B, C, D, A, B, C, and D. Now for the portion AB, the free body diagram would look something like this. Okay, the force towards the left side is 10 kilonewton, and again I'll have the same force towards right side as well, 10 kilonewton. Right, so the cross sectional or the diameter of this particular body is 25 mm. Right, so here delta AB will be given by P L by AE. I'll simply not write this formula every time. I'll simply write it here, PL by AE. The force is 10 into 10 to the power of 3 into length is 1000 into 10 to the power of 3 divided by pi by 4 into d square, that is 25 square into 2.05 into 10 to the power of 5. And now if I simplify this, I'll be getting 0.099 mm as the answer. Right, so again for the portion BC. Now for the portion BC, if I write the free body diagram here, so the diameter here is 50, the length is 600. Now coming back to the force. Now here we have a compressive load, but if I subtract this, meaning P, that is 34 minus 10, or 10 minus 34 will be minus 24. Right, so here again it is a compressive load. Right, so here that is nothing but 34 minus 10, which is nothing but 24 kilonewton. So this is also 24 kilonewton. I can either calculate from left or from right. So from right, so again I'll be having plus 16 minus 40, which is nothing but again minus 24. Minus represents here, that is a compressive load. Now here again, if I calculate the delta BC here, the load is minus 24 into 10 to the power of 3, this is because of compressive load, into 600 divided by pi by 4 into 50 square into 2.05 into 10 to the power of 5, and now which is nothing but minus 0.036 mm. Right, so here the minus represents there is a contraction or the material is getting compressed. So for portion CD, if I write the free body diagram, the diameter is 30, the length is 800, and the load is 16. This is again tensile load, 16 kilonewton. Now delta CD will be again equal to 16 into 10 to the power of 3 into 800 divided by pi by 4 into 30 square into 2.05 into 10 to the power of 5, and if I simplify this, I'll be having 0.088 mm as the answer. Now according to the principle of superposition, the total deformation in the body will be given by delta AB plus delta BC plus delta CD, so which is nothing but 0.099 minus 0.036 plus 0.088, so which is nothing but 0.151 mm. Right, so moving on to the next question. Alright, so we'll talk about a small derivation just to deal with how to derive or how to use differentiation in this particular kind of problem. Now they are talking about a wood pile driven into the earth, supports a load P entirely by friction along its sides. Okay, the friction force per unit length of the pile is assumed to be uniformly distributed over the surface of the pile. The pile has length L, cross section area A, and the modulus of elasticity E. Okay, let me just draw a schematic for this. So I'll assume this as the ground level, and there is a wooden pile that has been inserted. So this wooden pile supports a load of P, and now for this particular load we'll have reaction force given by the frictional force. The length of the pile is L. Right, so here I'll write another diagram here for my understanding. Okay, so if I have a body here, and now I'll choose a particular element, small element, from the distance y from the bottom, right? So I'll consider the thickness of this particular element as dy. Now for this particular element, so what is the total friction force? So dF will be given by F, frictional force per unit length, into the length, right? So that is dy. So if I want the total frictional force of the entire element, I'll have to integrate this. So total frictional force will be given by integral 0 to L of F dy. So which is nothing but F into L minus 0, again we'll have FL. Alright, so in equilibrium, so the load P will be equal to the total resisting frictional force. So again I'll have P will be equal to Ft, so which is nothing but P is equal to Fl. It turns, I'll have to write, I want the equation for F, so that is nothing but P by L, right? So I'll just keep this in mind, and now I'll have to calculate the resisting force until y. So whatever the resisting force that has been offered by these portion, right? So I want to calculate this. So to calculate this, again I'll be using PR will be equal to integral 0 to y F dy, back in the same original formula. So which is nothing but, for F I'll substitute this guy, again I'll have integral 0 to y P by L into dy, now which is nothing but Py by L. So this will be my resisting force until a particular distance y. Now if I'll write a free body diagram for the element dy. Now which is nothing but it looks like a square, or let's say a small strip. So for this, the forces acting on this particular body will be in compressive load. So what is that particular load? That will be PR. So the resistance force offered until the length y, right? So now the thickness of this particular element is dy, the compressive load is PR. Now if I want to calculate the deflection of this particular element, would be given as d delta will be equal to PR divided by AE into the length, that is dy. So now if I want the length of the whole body, I'll simply have to integrate again. So delta will be equal to integral 0 to L again PR. For PR again I can substitute Py by L, Py by L into dy divided by AE. Now which is nothing but delta will be given as PL by 2AE. Now this is what they've asked me to derive. Okay, now they've also asked me to draw some draw the stress diagram. So the stress, that is compressive stress, is given by axial force divided by A. Now the axial force is nothing but Fy, right? So Fy by A. So again I can write F as P by L, so that is nothing but Py by La. Now this y is the distance from bottom. Now I can simply calculate this Fc at particular points. At y is equal to 0, sigma c will be again 0. At y is equal to L, sigma c will be equal to P by A. Now stress graph will look something like this now. 0 and this is L. At 0 the stress is also 0. At L the stress is P by A. Right. So let me move to the next question. Okay. Now draw the diagram of normal forces, stresses and displacement along the length of the stepped circular bar ABC shown in the figure below. Cross-sectional area of AB is 50 mm square, BC is 100 mm square. Modulus of elasticity is 200 GPa. Okay, so with this given information, let me just try to solve the problem. I'll have to calculate the stresses, I'll have to calculate the displacements of all these things. So for this is a fixed element, okay, so there is no movement of A. Now I'll just write a free body diagram for AB. For AB, so I'll have a small circular rod, something like this. Now what would be the forces acting upon this? So this particular fixed plate would give some reacting forces on AB. So the reacting forces, what will be the value of this? Now here, if this is particular pulling this, again here also we'll have a pulling force. So RA and RA here. Now I don't know the value of RA. Now if the body is in equilibrium, so the forces will be equal to one another. So RA will be equal to 50, right? RA will be equal to 50 kilonewton. Okay, now with this I can solve for the stress sigma AB. So sigma AB will be given by load divided by the cross-sectional area, that is nothing but 50 into 10 to the power of 3 divided by the cross-sectional area of AB is 50 mm square. So which is nothing but 1000 Newton per mm square. Now delta AB is given by sigma AB divided by E into the length AB, so which is nothing but 1000 into 1000, the length is also 1 meter long, divided by E is nothing but 2 into 10 to the power of 5, so which is nothing but 5 mm. Now for BC, now the load acting upon this will be again in tension, so the load here is 50, so here also it will be 50. Now the length again is 1000 mm, so sigma BC again is given by 50 into 10 to the power of 3 divided by the cross-sectional area is 100, so which is nothing but 500 Newton per mm square. Now delta BC is again given by sigma BC divided by E into L, the length of BC, so which is nothing but 500 into 1000 divided by 2 into 10 to the power of 5, so which is nothing but 2.5 mm. Now so the total elongation of the body will be given by delta AB plus delta BC, so which is nothing but 5 plus 2.5, which is nothing but 7.5 mm. Now for the graphs, so firstly normal force. For the normal force, so if I have A, B and C here, at A again I'll have the force as 50 kilonewton, again at B also the same thing, C also the same thing, so a simple thing. Now for stress, so if I have A, B and C, at A the stress is 1000 Newton per mm square, so it will be same till B, and at B the stress will be dropped to 500 Newton per mm square, right? So coming back to the deflection, now if I have A, B and C, note that A is fixed joint, so there won't be any deflection at A, but at B the total elongation of body AB will be 5 mm, right? So here deflection something like this, and the total deflection or the deflection of body C will be 2.5 mm, right? So if I have this, again the deflection here will be 2.5, so something like this. So this is 5 mm and this is 2.5 mm. So this is how the total elongation of the body would look like. Okay, now moving on to the last problem of today's video. We're going to have another problem on composite bars. So composite bars is nothing but wherever we have a particular element made up of 2 or more elements, right? So here we have bar made up of copper, steel and again copper. Now let me just read out the question. What does that say? What do we have to do in this particular problem? Again, this is a fairly simple problem just to make our basics stronger. Now a steel rod of cross-sectional area 2000 mm square. Now cross-sectional area of steel is, I'll just list out all the data that is given in the problem. Of steel is 2000 mm square and 2 copper rods of each cross-sectional area 1000 mm square. Now for area of copper is 1000 mm square. Okay, together, okay, there's a typo. Together support a load of, the total load is given by 500 kilonewton as shown below. Find the stresses in the rod, so we'll have to find out sigma S, we'll also have to find out sigma C. Taking this modulus of elasticity for steel, I'll make that as ES as 2 into 10 to the power of 5 Newton per mm square, and EC is given as 1.2 into 10 to the power of 5 Newton per mm square. Okay, so with this particular data, let us solve the problem. Now, under equilibrium, whatever the force that has been acting on all of these particular body will be shared, right? So meaning that the load, the total load that has been applied will be shared between PC, that is this column, and plus PS, the second column, and again we'll have PC. Obviously, depending upon the modulus of elasticity, this load will be dependent, right? So either it might be high or low, don't know that, right? So P will be equal to 2PC, load taken by the two copper columns and the steel column, right? So here, if I substitute all the values, P is nothing but 500 into 10 to the power of 3 will be equal to P. I'll write it in terms of stresses again, 2 into sigma C into AC plus sigma S into AS. Now if I substitute the values again, I'll be having 500 into 10 to the power of 3 is equal to 2 sigma C into 1000 plus sigma S into 2000. Now if I simplify this, I can take 2000 as common, so I'll be having sigma C plus sigma S remaining will be equal to 500 into 10 to the power of 3 divided by 2000, so which is nothing but 250. Right, I'll call this as equation 1, and now I'll have to use the principle of superposition, which is nothing but the total elongation of the entire thing will be equal, right? So which is nothing but elongation of steel will be equal to the elongation of copper, because all of them are applying on a same steel plate. So here this is end is fixed, so this entire total plate will be moved equally with all of these bodies, meaning the deflection will be equal in all of these columns. So I'll only consider steel and copper. I'll compare these two. So the delta can be written in terms of stresses, that is sigma S divided by S into the length LS. Again, that is equal to sigma C divided by EC into the length of copper. Now sigma C I don't know, sigma S I don't know, ES they have given us 2 into 10 to the power of 5, and the length of the steel rod is again 300 plus 100, that is 400. Now we have 400 here. It will be equal to sigma C, we'll have to find that out. This is given as 1.2 into 10 to the power of 5 into the length of copper is again 300. Now if I simplify this, I'll be having 0.8 sigma S will be equal to sigma C. So this will be our equation 2. Now if I substitute this equation 2 in 1, I'll be having 1.8 sigma S will be equal to 250. Now sigma S will be given as 250 divided by 1.8, that is 138.89 Newton per mm square. Now again if I substitute if I subtract this back, sigma C will be given as 250 minus 138.89, I'll be having 111.11 Newton per mm square. Now thank you for watching thank you for watching our video. Hopefully this has been helpful for you. Happy learning. Stay tuned for the next video, and bye bye.